Hi guys, welcome back. Welcome. Happy Saturday. We are going to continue our discussion of our CCIE topics. Today we're going to talk about redistribution. And we've already kind of gone through some of the basic concepts. We did IPv4 route redistribution overview and basic redistribution examples. And now we're going to talk about why routing loops occur. And what is it that we can use? What kind of tools, what kind of methodologies can we use to identify whether or not a loop has occurred, or how can we prevent those loops? And then that's going to be a brief introduction. So we're going to go through these two lessons today. I've kind of expanded on this a little bit. And then as we move down into our final discussions of redistribution, we're going to get into some pretty detailed examples. Create some scenarios where we have suboptimal routing, data plane and control plane routing loops that are occurring because of redistribution. We'll talk about how we can control the redistribution process and so on using route maps and filters and prefix lists and access lists and so on, or manipulating things like administrative distance, and which techniques are best used for preventing routing loops at the control plane or routing loops at the data plane, because the behavior of a control plane routing loop is a lot different than the behavior of a data plane routing loop. So we'll take a look at that. We're going to introduce that concept in this lesson, and then we'll continue to expand on those concepts as we go into some of our future lessons as well. The topology that we're going to be using for today's discussion is a little bit different than what we had in the previous discussion. Just a basic 4-router topology where we have Ospf and RIP running. It's already pre-configured. I'll save this in the Google Drive for you guys under the routing loop topic, so you guys can take a look at this. But we'll take a look at some other examples as well, and I'll probably either apply some different configurations to this topology or expand on this topology so we can kind of go into some of our more advanced discussions on route redistribution. So our first lesson is, why do routing loops occur, right? Why do routing loops occur in the first place, right? Is it because of poor design? Is it because of poor implementation? Is it just because the nature of the beast, if you will, and so on? So we're going to talk about the differences between, say, a control plane routing loop and a data plane routing loop. Which is what's the difference between a metric-based routing loop versus an administrative distance-based routing loop. This is an example here where we're going to see issues with redistribution because of an administrative distance routing loop rather than a metric routing loop. But in some of the other examples that we'll see later on in our next few lessons, we'll talk more about some of those in detail. All right. How do we identify routing loops in the topology? Typically, you want to try to, of course, identify those routing loops prior to implementation and prior to the configuration. You should be able to look at a topology, for example, and be able to identify where problems could occur without having to go into actual active troubleshooting. So we will talk about that. What are some of the different tools that we can use to identify those routing loops? And why are those loops occurring at the control plane or at the data plane, right? Redistribution causes, as we talked about in our previous example, loss of end-to-end route calculation. And because of the incompatibility between the different algorithms that the different protocols use, we also lose our loop prevention techniques that are built in. For example, dual is not compatible with the shortest path first algorithm. And the calculations, right? In SPF, we would use some sort of method of resolving a loop-free tree. And then in the diffusing updates in EIGRP, we would use things like feasibility condition to ensure loop-free redundant paths and so on. But the feasible successor, feasibility condition, those concepts that we talk about are different than how Ospf handles resolving the tree and calculating destinations. Okay, so we have to understand the impact of taking routes from one routing domain and sending them into another routing domain. Since we're transferring information between the different protocols, and because those calculations are not compatible with one another, we essentially lose the ability to guarantee a loop-free path between those two different protocols. Now, there is a case of a redistribution example where routing loops could not occur, right? We'll talk, and this is not one of those examples. If we had, for example, just a single point of mutual two-way redistribution, right? Where I have a single router that's running Ospf and EIGRP, and I'm doing a bidirectional redistribution on that single router, we're not going to see a routing loop in that particular case, right? Even if there is a loop in the control plane, there are protection mechanisms in the internal routing process to prevent loops from actually occurring in that particular scenario. The only case where we actually need to think about the problems is if we have multiple points of redistribution and maybe where there might be multiple meeting points of the same protocol. All right, so keep this in mind, of course. If you're in the lab topology, you want to try to recognize those points and just make note of them, because you may end up having to try and resolve some sort of issue with that redundancy and that redistribution in that topology. Doesn't always mean that there's going to be an issue, but there could be. You know, one of the things that I made note of to mention in this particular class is that because the topology in the CCIE lab is so vast, it's not always about optimal routing in the topology. In a lot of cases, they want you just to be able to resolve destinations. They don't necessarily care about whether those resolutions are the best or most optimal path. And there's so many different aspects of the topology that you can't really enforce all these different rules to affect the most efficient routing in the topology. So we just want to make sure that routing can occur in a lot of cases. All right. The other problem with redistribution issues, where we're getting some sort of control plane or data plane loop, primarily control plane, is that it's not always going to happen, right? There aren't really any kind of basic general rules that you can apply to say, okay, if I do X, Y, and Z, I'm definitely not going to have a routing loop, right? Because every case of redistribution is going to be unique. The topologies are going to be somewhat unique, and so you can't really apply, say, a golden rule to the redistribution process. For that reason, we just have to be able to have a good understanding of what to look for and how to evaluate the topology visually, and then also how to run some different tools to be able to make sure that routing loops are not occurring. All right. So we can look at, in this case, specific cases where loops can occur. We'll, of course, create topologies where loops are occurring, and we'll go through the process of trying to fix them. All right. Loops can actually occur for a couple of different reasons. Maybe it's the wrong path has a lower metric than the correct path, so I end up preferring a suboptimal path. Or maybe the wrong path has a lower administrative distance than whatever the correct path might be. So I would have to kind of look at and manipulate administrative distance values to be able to identify whether or not there's a problem in the topology. Okay? If a route, say, comes in from RIP, right? In this particular case, that's kind of what we have in this diagram. A route comes in from RIP and it gets redistributed into Ospf. The AD of Ospf is going to be lower, so RIP is going to then choose the route through Ospf. That's a concept that we're going to go ahead and demonstrate in this particular case. I might even add to this topology to make it even more complex of a design scenario where we actually see some issues, right? We'll see how much time we have after the lesson here. All right. We are going to take a look at both the data plane issues and the control plane issues, because each of those issues do have different solutions to the problem. All right, so let's start by talking about a control plane loop. Control plane means that we're trying to converge reachability, not necessarily routing packets, but learning information, right? Whenever we talk about the control plane functionality, we're talking about routers exchanging routes, routers originating routes, and so on. So in the case of a control plane loop, what's occurring in this case is that you might have a scenario where essentially you get the churning of the routing table, right? That means I advertise a route to you, and then I withdraw that route, somebody else advertises the route, and then those routes churn and thrash in the routing tables indefinitely. And it might even result in the incrementing of metrics and so on to the point where networks become unreachable. That's what we call the counting to infinity problem, where metrics keep increasing as each router advertises a route or takes control of a route. And then the destination eventually becomes unreachable. All right. Now, initially, there could be partial reachability. There could be partial reachability in the case of, say, for example, one router that actually owns the route is claiming the route. And so we get reachability in that case. And then secondarily, another router starts to claim a route and we lose our reachability in that case, and so on, right? Packets could be potentially delivered in this case. If the control plane is correct, then the packets will be delivered. If the control plane is not correct, then the packets obviously won't be delivered. So in a real design, the end result might be just partial packet loss. Maybe we have 98% reachability, but then there's that 2% where it's not reachable. All right? So we have to look at the network, in this case, to be able to effectively troubleshoot at the exact moment that the state of the control plane is wrong. That's obviously going to make it much more difficult to track down or identify that particular type of loop. It's also, by the way, more difficult to simulate in a test environment for learning purposes. So I'll see if I can come up with a scenario that allows us to identify this type of control plane problem. It's obviously going to be a lot easier to create some sort of data plane problem than a control plane problem. But we'll see what we can do. Maybe I'll come up with a scenario that where we can actually simulate this control plane problem. All right. Now, there's going to be a whole bunch of tools, obviously, that you can use. Tcl scripts, Tcl ping scripts could be one of those tools. And we'll take a look at some of those advanced tools over the next 3 lessons as well. All right. So in data plane loops, it's a little bit different, right? Now we're talking about the packets that are being routed across the network. The control plane in this case is stable, but it's stable in the wrong direction. So packet forwarding in this case would get looped. This is a much easier thing to track because most of the time, say almost all the time, you're going to end up having no reachability and 100% packet loss. So now we can kind of go in and do our trace routes and do our pings and look at routing databases and so on. And we can identify what the potential issues are using various tools. And I'll introduce maybe one of those tools in this case. We'll actually go through one single scenario where we actually get an administrative distance control plane routing loop. And we'll go ahead and try to resolve that. In our case, it'll just result in a suboptimal routing path. But that's actually not a horrible thing, but it could be in a larger topology. All right? So the reachability test in this particular case in a data plane loop is usually going to show us if something is wrong. But the first step in any implementation or design is to make sure that you can identify the routing loops in the topology. We need to visually trace the route advertisement path And ideally, and hopefully after our next few lessons, you guys will be able to look at a topology and you'll have the ability to identify the loops before the implementation and before those loops occur. I don't recall in my lab scenario that they introduced any kind of, in the troubleshooting component, any kind of redistribution issue in my particular example. I did have to do a redistribution implementation, and I had to use bitwise masking to be able to identify what routes were redistributed into the domain, but I don't think I had a scenario where they actually introduced, in the troubleshooting section, they introduced an issue with a data plane or a control plane loop. Not to say that you won't get that in your case. So we need to make sure that we're completely aware of how all this works. All right. You really should get to the point where you can look at a topology, for example, this topology on the screen, and you can easily identify, just by looking at the topology and understanding how the routing processes work, you can easily predict and identify that there's going to be an issue in this particular case. Because we know the administrative distance of RIP is 120. We know the administrative distance of OSPF is 110. So how is that going to affect us, right? Am I going to prefer the OSPF route over the RIP route, and so on? All right. All right, so I'll introduce a couple of tools. There are some tools that you guys are obviously familiar with, basic tools like traceroute and reachability tools like ping and so on. But there are also other options available. We can use Tcl ping scripts. We can do debugs for IP routing. We can do IP route profiles and take a look at IP route profiles. Or we can actually do the most basic thing, which is just a basic trace route to see what's happening in the topology based on the trace route. So there are lots of tools that we can use. Like I said, a lot of these tools you're probably familiar with, maybe some of them not so familiar with. It just depends on what scenario you're faced with in the lab. And obviously you want to be able to shoot from the hip based on your experience to be able to identify which method you're going to use to troubleshoot that particular problem. All right, so I won't use too many of those tools in this lesson. We're just going to look at some basic tools and basic solutions, but as I go through the next few lessons, I'll get more in depth into some of the other tools that you can take a look at. All right, generally when it comes to troubleshooting on the test, it's going to take much longer to understand the overall routing process than it would to be able to maybe use some of these tools to identify a particular problem, right? So oftentimes you just want to make sure that the redistribution is implemented correctly. And that would involve the use of potentially like route tags or route tag filtering, changing administrative distance values for a particular prefix, or a neighbor relationship for a particular protocol. And we'll spend some time talking about those tools because I'm going to basically make the assumption that up to this point, you actually don't have the ability to predict what's going to happen in the topology. All right. So the first tool that you have available to us, we've used it a couple of different times in our network, is Tcl Scripting. Right? It is a full programming language, and there's lots of documentation and lots of information available online about Tcl scripting. In fact, if you go to tcl.tk, you can get all the open source information about Tcl scripting that Cisco runs. I mean, it's open source, so it's not unique to Cisco in this case. But tcl.tk will give you a bunch of documentation and information about Tcl scripting. All right, 99% of the Tcl functionality that exists, we don't need. It's not really applicable to what we're trying to accomplish, and it's kind of outside the scope of the lab itself, right? But that's okay. certainly doesn't hurt to be able to understand how this scripting works and what the effect of Tcl scripting is in our topology. So I'll just do a quick review of a Tcl ping script, and you can obviously get much more involved. It is an open source language. It's been supported in iOS for many, many years. I believe that they're supporting version 8.3 or something like that at this point, 8.3.4 or something like that. But it's a really useful tool for the redistribution, in redistribution for automating things like ping scripts. All right. There is a book you can actually get. It's called Tcl Scripting for Cisco iOS. I'm sure you can find it on Amazon. I tried to find an electronic version for you guys, but I have to admit I didn't really search that hard because it's really, really involved, and it's not necessary really for you guys to understand that level of detail. All right. I mean, you can get extremely granular with Tcl scripting. I'm sure some of you guys have played around with it before. All right, so let's take a look at kind of just a basic Tcl ping script. I'm just going to use this as a reference, this command line. So we're going to go into the shell by just typing Tcl sh. You notice the prompt will change to our, what I call Tcl prompt, Tcl prompt. And then we're going to create a loop where what we call a for loop, and we're going to create an array of variables, right? So a for loop allows us to identify, depending on what our command line action is, an action against a particular variable. So we say for each x, in this case, x is the variable in the array. We're going to open that array, and now we can input the values. So I can say, for example, 1.1.1.1, 2.2.2.2. Oops, let me Tcl quit that and try that again. Tcl quit. Why isn't that working? Now let's do it that way. All right, let's try that again because I mistyped. All right, so we'll say for each x 1.1.1.1, 2.2.2.2, 3.3.3.3. These are all the loopbacks in our particular topology. And you can actually do this in Notepad or something like that. Cut and paste, or you can cut and paste from command line if you've got to maybe grab a show IP interface brief and so on. Thanks, Chris, for sharing the link for that book. If you're interested, it's a pretty interesting book. I mean, I've glanced at it a couple of times. So we created our array using variable x, and now we have to essentially do our exec command, right? And in this case, we're going to do just a basic exec command, which is our ping. So we're going to close the array, and then we're going to do ping string x, which allows us to identify the action that we're going to take against the variable. Of course, it's not working now. Close the array. Sorry about that. So we got some syntax issues here, but it looks like obviously with Tcl scripts, as I mentioned, you got to have the syntax has to be exact. It's a coding language. So you have to be really familiar with how the language works and the syntax, even the spacing of that and the order of operations. So we were able to complete it finally. So go into the Tcl shell. For each, in this case, I create a variable of address. And this is my array, the 4 loopback addresses that I'm going to ping. I close the array, and then I execute my command, which is going to be to ping that particular address. So this is I guess by the time I could have just done ping to those 4 addresses, it would have taken less time. But if you're trying to execute more extensive commands, right? You're trying to execute kind of more you know, with different arguments and maybe different variables, it might be more useful to run a TCL script to do that. But like I said, the syntax must be exact. All right. You can write more complicated logic, but in the scope of what we're trying to accomplish here, you don't really need to spend a lot of time, because all we're doing is basically testing things like reachability. But you could execute trace routes. You could actually set up a script, for example, that sends a text message or sends an SNMP trap if a particular result is realized or a particular event occurs. There's all kinds of interesting things you can do. I'm not an expert in TCL scripting. I don't really use it that much, but it is a tool that's available to you. All right. There will be some other tools that I think are probably more useful and quicker to be able to understand what's happening in a particular domain. If you're having a loop, if you have a loop or have some issue with routing, and we'll talk about that in some of the other future lessons that we're going to have. Okay. All right. There is actually not really any good documentation that falls within the scope of how you would use TCL scripting for the purposes of the lab. You would have to kind of filter through all of the documentation at tcl.tk, but you know, that's not something that we're going to spend too much time with. All right. So as far as preventing routing loops and routing feedback, right? What are the strategies that we have to employ to prevent those routing loops and routing feedback? We have lots of other tools at our disposal as well. We're going to just use this topology here as an example. This topology here is an example of identifying what one of the issues is with this redistribution example and how we can quickly identify. It's very easy. In this case, a trace route will be useful, but I'm going to run through a scenario where we kind of go through a couple of different verifications. The big thing to think about is where in the topology are multiple routing protocols necessary. That's a very important concept to understand. We need to be able to identify easily where those multiple protocols are required, and then in turn be able to identify where potential problems might exist if we're doing redistribution. There is one, even though I said there really aren't any kind of golden rules for best practice implementation, there is actually kind of one golden rule, and that is we always need to protect the higher AD routes on a router if we have two routing protocols meeting or converging at multiple redistribution points. And in this case, with RIP, we've got 120. With Ospf, we've got 110. So we need to protect RIP in this particular case. There may not be a problem, but there could be a potential case where wrong decisions might be made based on the topology. And it really does. It's a case-by-case basis. Like I said, there really aren't any general rules that you can apply. But you should be able to recognize, based on your understanding fundamental principles of the protocols themselves, your understanding of those protocols, you know, where potential problems might exist. Our example in this case is RIP and Ospf, where we could see a problem. The issue that we have in this case, and we'll walk through it, is that the higher AD routes have a chance of potentially getting fed back, but the lower AD protocol, which is providing the routing feedback, might not be making the right decision. So we have to make sure that the routers that are attached to the two different routing protocols are always going to prefer the routes towards the source protocol. But in the case of this issue, that's not going to be preferred. All right. The lower AD in this particular case is always going to take preference. There are some cases, of course, where we have routing, but it may not be optimal routing. And our goal is to prevent suboptimal routing, right? Now, within the scope of the lab, like I said, there could be potentially lots of different ways to reach a particular destination. And the main focus of the lab is, in fact, reachability. But there may be scenarios where, specific scenarios where they may actually challenge you to identify not only that there is reachability, but what is the best reachability. All right. And we can see metric-based loops. We can see administrative distance loops and so on. Like I said, that's a difference between, say, data plane and control plane, where metric-based loops, and we'll see these in some of our later discussions in some of our other lessons next week. Those can be typically fixed by doing some sort of ACL, maybe a prefix list, maybe some sort of tag filtering, and in rare cases, you might be able to fix metric-based loops by manipulating administrative distance, at least on a per destination basis, right? But administrative distance loops can really only be fixed with one problem, with one solution, and that's by manipulating the administrative distance. We can't, for example, fix an administrative distance loop with a route tag, okay? There is another basic rule. Don't ever allow routes that originate from protocol X to be fed back into protocol X, right? That's where you're going to start to see the loops and maybe some deleterious effects in the routing. We can stop that typically by using a distribute list at the interface level or at the process level. We can do some sort of metric filtering, but we always need to be able to identify the problem to start with. All right. Now, there are some automatic tools that exist. We won't see them in this lesson, but I'll show you these in the future lessons, right? For example, if BGP is redistributing routes into an IGP. If I'm taking, say the green area here was BGP, and this was OSPF or RIP at the bottom, and I'm taking BGP routes and I'm sending them into RIP, BGP automatically tags those routes with the BGP autonomous system number that they're coming from. Now, that could be useful if you have multiple BGP autonomous systems or multiple points of inflection where you have multiple redistribution points. In this case, the tag might be the same, so it may not solve our problem exactly, but that's an interesting concept about BGP, is that it will automatically tag, apply a route tag to a route that's being redistributed from the BGP process into the IGP protocol, right? The route tag is just basically an identifier of the route itself. We can apply route tags through the use of route maps and so on. We'll actually do that in one of our future lessons here. All right, because we can actually take those route tags and then we can match them with a route map, and then we can deny redistribution based on tags to avoid feedback into the routing domain by saying, hey, this route was tagged X and it was redistributed from protocol 1 to 2. I'm not going to then redistribute any routes tagged X from protocol 2 to 1. Okay, so let's start to take a look at the example here and take a look at how we can resolve this. I mean, this redistribution process is a pretty basic redistribution process. And you guys already have a basic understanding of how redistribution works. But let's go ahead and take a look at the process on router 1 and router 2. So if I go into router 1, and let me break out of that. My TCL quit for some reason doesn't work there. I'm sure if I was using iOSV, it would have probably worked a little bit better. The spacing was an issue regardless, but I think with this particular version of iOS, NGNS3 doesn't quite work the same. So let's go ahead and just do a show run pipe section router. Just to verify basic operation, we've got OSPF process ID number 1, and we're redistributing RIP into OSPF using the default metrics. We're not sending them in as E1. They're going to have a cost of 20. So very, very basic redistribution from RIP into OSPF. Remember, when you're redistributing from a distance vector routing protocol, you need to specify the subnets keyword, because if you don't, only classful networks will be redistributed and your subnets will not be redistributed. All right. Now, as far as the RIP side, we're redistributing OSPF into RIP. And again, remember, when you're redistributing into distance vector, you have to specify a seed metric. So in this case, we applied this seed metric to the redistribution process. We're saying, okay, take the routes from Ospf, redistribute them into RIP using a seed metric of 3. All right. We'll go back to router 2 here. Remember, that's our second redistribution point, router 1 and router 2. There's some loopbacks back here that allow us to simulate some networks. And then there's this fast Ethernet link between the two routers. I should have put the subnet on there. Show IP interface brief. So that is, that fast Ethernet link is 155.1.12. So that's the link between router 1 and 2. And then this is the link between router 2 and 4 and so on. Okay? But if I do a show run pipe section router, I can see, again, very basic redistribution process. In fact, it's kind of identical. All right? So we know that we can have routing loops. That's the whole point of this discussion. And we also know that they may not be visible right away. In fact, we look at this. I did my ping to all my loopbacks. I was able to reach all my loopbacks using that Tcl script. And I was, I had full reachability, right? But does that mean that it's the most optimal reachability? Okay. The issues don't always manifest themselves dramatically, where you get packet loss and so on. All right. Now, I can use tools like traceroute, like I said. I can do debug IP routing, and that will allow me to identify how packets are being routed. All right. Route feedback is a term that you definitely need to be familiar with. That's when a redistributed route gets redistributed back into the same protocol from which it originated, which can also happen very easily, right? There's nothing in this redistribution process that we have configured here that says, hey, by the way, don't take those routes that you put into RIP from Ospf and send them back into Ospf, right? RIP doesn't actually distinguish between routes that come externally versus routes that are learned internally. All the RIP routes look the same. All right. So I guess the question is, how do we define how believable a prefix is? All right. First, we have to know that only some prefixes are going to be compared. As far as routing goes, this is what we talked about in our first lesson. For example, 10.14.1.0/24 and 10.14.1.0/25, those aren't the same prefixes. And in the case of any kind of routing decision that we're going to make, the longest match always wins. But if we are comparing two same prefixes from different routing protocols, so 10.14.1.0/25 and 10.14.1.0/25 from a different routing process, we know that AD is going to be used to determine which one's the best, and the lower AD in this particular case wins. If the AD for some reason is the same, because these can be manipulated and changed, and we didn't talk about this actually in the last time, but if I've gone in and I've adjusted the administrative distance of EIGRP to match Ospf, and now we're learning about the same route through two different processes, the same prefix length, two different routing processes with the same AD, guess what the tiebreaker is, right? The tiebreaker is based on the default administrative distance of that particular routing source. So Cisco will always go back and say, well, normally EIGRP is going to be trusted more than Ospf, even though you've manipulated those values. I'm going to go ahead and make sure that I trust EIGRP. All right. We also talked about the fact that external routes should always be less trusted than internal routes. EIGRP, for example, does this by setting the administrative distance of 170 for external routes, but 90 for internal routes. But there are some other routing protocols that don't do that, right? RIP doesn't distinguish between external or internal at all. Ospf does have a way of distinguishing based on the LSA type between external and internal routing, but it uses the same administrative distance value for all types of routes in Ospf. All right, 110, right? Now with OSPF, we do have the ability to manipulate the AD for external routes separately than internal if we want to. That is an option. Okay. RIP doesn't have that possibility. So, like I said before, routing loops are generally going to occur when we have redistribution between a protocol with a higher AD and a protocol with a lower AD, and that's essentially what we've created in this particular case. This means in our particular diagram here, we go back to the diagram, in our particular diagram, RIP is most often going to be involved in routing loops since it has the highest AD of all of our IGP routing protocols. All right. So let's look at our topology and maybe see if we can identify where potential routing loops can occur. First thing is to understand what networks are participating in what routing domain. We obviously have different colors here to identify where redistribution occurs. We got two different routing domains. The serial links and the loopbacks on the northbound routers are in OSPF, and the Ethernet link and the loopbacks are in the RIP routing process on the southbound links. But we are doing mutual redistribution on router 1 and router 2. The issue here is that we'll have suboptimal routing. That's really what we're going to try to resolve. So let's do a show IP route and a trace route from router 1 to router 2's loopback. All right, so let's do, first of all, show IP route 2.2.2.2 on router 1. All right, we can see that we're learning about 2.2.2.2 via RIP. Administrative distance is 120. That's actually correct. Hold on, I may have to make a modification to this topology real quick because I just realized we're not actually getting that through OSPF. Hold on one second. Sorry, sorry about that. I had the configuration in place correctly. I just forgot to add a cable between R3 and R4. So these fast Ethernet 00 interfaces were created. I just didn't plug them in. So naturally, we're not going to be going the right direction, or the wrong direction in this case, what we're trying to demonstrate here. So now that I fixed that, you could see before we were using, obviously, the RIP route to reach that particular destination. But as we converged, you'll notice that for the 2.2.2.2 entry, we decided to take the OSPF route. Now, if you look at our topology here, the 2.2.2.2 loopback is here. I don't want to go all the way up to router 3, then over to router 4, and then back down this serial link to router 2 to reach that destination. But that's the issue that we're talking about here, right? That's the issue that we're faced with, is that because of administrative distance values, we decide to take the path from up to router 3, over to router 4, and then back down to router 2. In fact, if I come over here and I do a trace route to 2.2.2.2, we can see that we're going up to router 3, over to router 4, and back down to router 2. So we're going all the way around, even though we have a direct path to that destination through RIP. All right. Now we know why this is happening, right? RIP has a higher administrative distance value than OSPF. But there are a couple of ways that we can actually fix this. In the lab itself, you actually would not fix this unless they specifically asked you to fix suboptimal routing, right? And like I said, in a lot of cases, they may not do that, all right? But obviously, in the case of a real-world design, this is something we would want to fix. We don't necessarily have a loop. It's just not the best path to take. And that's because OSPF is not setting a higher administrative distance value on its external prefixes. So we have to kind of force this to happen manually. And there's a couple of ways we can do this. I can actually, if I go back into my router 3 and router 4, if I do a show IP route OSPF, pipe include E2, we can see the 2.2.20 subnet, which is the loopback behind the router on the right, router 2. It's coming in as an OE2 route, but the administrative distance of this route is 110, which means that router 1 is learning about that route through Ospf. Conversely, router 2 is learning about the response. So if I go into router 2 and I do a trace route to 1.1.1.1, we would see exactly the same scenario. I'm going up to router 4, going over to router 3, and coming down to router 1. So one of the solutions would be to simply modify how Ospf treats external routes. We can go into our global configuration mode, go into router Ospf, and simply say distance for Ospf process ID 1. Actually, we're already in the process, so let's just do external. And let's go ahead and just make it slightly higher than RIP. So like I said, in Ospf, we do have the ability to apply different administrative distance values to intra-area routes, inter-area routes, which are my type 3 LSAs, and external routes. All right, now I'm only going to do this on one side because I also want to demonstrate that we could have routing issues if we don't have a symmetric configuration. So if I do my trace route from this side, I can see I'm going from router 3 to router 4 to router 2 to reach that destination. But if I go into the router 2 side, it should have modified the distance there.
Hey Scott, what's the difference between inter and external for that?
The difference here, oh, I didn't execute the command. I thought I'd executed the command. I think I did a backspace and I didn't execute the command. The difference here is that this is type 3 LSAs. These are the routes that are coming from one Ospf area to another. These are within the area. So these are my type 1 LSAs, and then these are my type 5s and type 7s, right? That's the difference there. But I don't think I actually executed the command. Let me see. So do show IP route pipe include E2. So we can see now that the administrative distance here is 121 for that particular path. All right. Except for I'm doing it on the wrong router. That's why. Router 3 is a transit path, right? It's not the router that's making the decision at the boundary. So we certainly would want to be consistent and apply this to all the routers in the Ospf domain to make sure that they all interpret the graph the same way. But in order to actually affect the routing process, I would actually have to do this on the router that's making the decision and that understands the route from both perspectives, right? It understands the route from RIP and it understands the route from Ospf. So router Ospf 1, and we're going to do distance. Did that answer your question, Tim, by the way? As far as the difference between these three? Maybe? Okay. Certainly the external ones are the ones that are coming from a redistribution process. You can modify the distance of the internal routes, the type 3s and the type 1s, but it's not really going to affect the overall routing process, from a boundary router perspective, where we're doing the redistribution. So we're going to say external 121. All right. Now if I do my trace route, you should see that eventually it should prefer the RIP route over the Ospf route. There it goes. So now we're preferring the RIP route over the Ospf route. Oh, that's okay.
Hey, Scott?
Yeah, I got you now. I saw you said you couldn't unmute.
Can you look at the topology again?
Sure.
Can you bring that up?
Yeah, absolutely.
The answer sounded, it made sense, but what I was confused about is if everything is in area A, how is that considered like external?
External routes
For
would be
OSPF.
coming from RIP into OSPF. Remember, whenever we do any redistribution, those come in as external routes, right? Type 5s in this case, because we don't have a special area.
Right, where I guess what's confusing me is if we're trying to go from router 1 to router 2, wouldn't it automatically, I mean, wouldn't we need to change the administrative distance for OSPF? And that way RIP, it'll actually route across instead of going all the way over like what you're saying. But if you make it external, I mean, this to me looks like an intra-area network.
So I understand what you're saying, but you have to understand that the routes are coming in both directions. So if you, let me put this in a snippet so I can kind of draw in here and show you what I'm talking about. So let's say we got this loopback, right? I'm learning this loopback through RIP with an AD of 120. Okay, now if you look at this from the perspective of one direction, I'm redistributing that loopback into this domain, and it's going to come in as an E2. That's an external 2, but that has an administrative distance of 110. That route is going to be propagated to router 1. So router 1 is going to choose that path because it has a lower AD. So if I can make this 121, we still have an alternate path, but I'm going to choose the RIP route over the OSPF route. Does that make sense?
Yep. Thank you.
Okay, no problem. But I only did it in one side, right? So now if I go to router 2 and I do my trace route to 1.1.1.1, router 2 still believes that the best path to reach that external network is to go through the OSPF domain. And that's because if I do a show IP route 1.1.1.1, we can see that we have an administrative distance of 120. It's still an external type 2 route, but we have an administrative distance of 110. So you want to make sure that, and that's another issue you may run into on the lab or even in a real design scenario where you have some configurations applied at some points in the network, but not at all points in the network. So we want to make sure that we come into our OSPF process here. Distance, OSPF, external, 121. All right, and again, if I do my trace route, trace route to 1.1.1.1, eventually as I converge, I will now choose the optimal path. So now we're going directly to router 1. That's just one example, right? And this is, like I said, this is more of a control plane loop. They call it a loop, even though we're not actually creating a loop, than a data plane loop, because it just means that we're preferring an alternate path that's not the best path. Okay, because now we're going to take the direct path. Remember, AD is also a local setting. I was setting it on router 3 because I was on the wrong tab. Setting the AD on router 3 has no effect on what router 1 and router 2's decisions are. So we don't necessarily have to establish this on router 3 or router 4. We don't need to configure this on router 3 or router 4. It's not going to affect their relationship because router 3 and router 4 are internal routers within the OSPF domain. So they're just going to choose, based on reachability to the ASBR, they're going to choose the optimal path to reach that particular destination. Router 3 will go down to router 1, and router 4 will go down to router 2. All right? We can also, so this is going to affect, say, for example, the administrative distance for all the routes. But what if I didn't want to affect the administrative distance for all the routes? What if I wanted to only affect the AD value for a set of routes? Maybe I do want some of the routes to take a suboptimal path, and I want other routes to take the optimal path. We can do this by creating an access list, or we could use prefix list. Access lists are pretty typical in this particular case. And then we can apply the process to apply administrative distance to a particular set of routes based on that particular access list. So let's say, for example, we don't care necessarily about the 2.2.2.0 subnet. So let's go into router 1. I'll go back to the diagram and kind of explain what we're trying to do here. So I'm going to go IP access -list standard, and we'll just call this RIP2. And we're going to permit 2.2.2.0. So that's the actual prefix that we're receiving. And then we'll go into the RIP process, router RIP, and we're going to say distance 109. And we're going to match essentially any route in this case. So we're applying a distance to any route, but only based on what's allowed by access list RIP2. All right. So if I look at the route for 2.2.2.2, do show IP route 2.2.2.0, we can see that we've applied an administrative distance specifically to that particular prefix. That would have been another way of kind of getting around this issue with the RIP routing. So for example, if I go into router OSPF1 and I do no distance external OSPF, what did I set it at? 121? No distance OSPF external, 121. All right. So what we should expect is that particular, now we're not overriding the administrative distance for OSPF. We should expect that the OSPF route would have been preferred. But again, if I do a show IP route 2.2.2.0, I'm still preferring the RIP route because 109 is less than 110. So you wouldn't necessarily apply these tools consecutively, but let's do it the opposite way. Let's go back into router OSPF and let's go and put in our distance for external to 121 and do show run pipe section RIP. And for the 2.0 subnet, so right now if I do a trace route to 2.2.2.0, I can see it should be taking, 2.2.2.2, it's going directly to router 2. And that's because of this distance 109. So I'm going to say distance, in this case, 122. All right. Now if I do my trace route to 2.2.2.2, we should see eventually that it should take the OSPF path. Do show run section router. Should take the OSPF path because, oh, it didn't take it out. I guess I have to remove it first and then reapply it. So let's remove it and let's reapply it. That's interesting. Why is it not taking it? Router RIP. No distance. To show run section RIP. Okay. Distance 122. Do show run section RIP. There we go. It's weird. I might not have been in the RIP routing process. It should have given me a syntax issue, but all right, do trace route. And let's do a show IP route 2.2.2.2. So we're getting an issue with RIP. RIP routes tend to stay in there for a while. Let me do because of the hold downs, clear IP route star and see if we should. Okay. So now we're getting it through OSPF. 122 there. Do trace route. Yeah, that's the right behavior. I'm curious why it's saying 122 here, though. We didn't apply 122. Oh, you know what? I was in the routing process. Check it out. Section router. So here's an example. I did this on purpose, by the way. No, I'm kidding. Here's an example where we have this same administrative distance applied to Ospf and RIP for that particular prefix, and it's preferring the Ospf route because by default Ospf has an administrative distance value of 110 and RIP has an administrative distance value of 120. So I was in the Ospf process when I tried to apply that. So let's go ahead and take that out because we should be seeing a 110 there. Router Ospf 1, and let's just take this command out of here. All right, now if I do a show IP route 2.2.2.2, I should see a distance of 121. Right, that's what I would expect to see. Right, because again, that's the value that we applied in the routing process. Right, right here, distance Ospf external 121. Now, what's interesting about this is you can get really creative. So if I go into router 2, for example, section RIP. I think I have the 2.0. Yeah, so let's go ahead and create a show IP interface brief. Show IP interface brief. Let's create another loopback. We'll call it loopback 22. And I'll put an IP address of 2.2.3.0 or 3.2 on that interface. So it should automatically include it as part of the RIP, and then of course it would be redistributed. So if I do a show IP route, we can see that we're getting the 222 network and the 223 network, but one is going through Ospf and the other is going through RIP. So this guy has an administrative distance of 120, so that's the normal behavior. This guy has administrative distance of 121, so that's the normal behavior. And I could get really creative. I can apply different administrative distance values to different prefixes and so on. I doubt that you would ever see anything like this in the lab where they get so specific because there's so much they have to test you on. They're not really going to have the ability to test you on, every specific option. But you could get pretty creative by just manipulating administrative distance values when you're doing multi-point redistribution to be able to affect how packets are routed through the topology. All right. We'll see more options later on when we start to get into route maps and doing route tagging and so on. So for the 2.2.2 route, we have an administrative distance of 109 for RIP. That's going to beat the default of 110. We're certainly going to beat 121. So the 109 would be preferred over the 120, 110 or 121. All right. Presently, it's 121 because we're manipulating the external routes for Ospf for the AD as well. All right. There is another way to do it. For example, you could create a standard access list where you deny the 2.2.2.0 subnet and permit everything else. And then you could also, maybe, actually, let's do that. So let's say, for example, let me go ahead and kind of get back to my default configuration. All right, so I'm going to get rid of the manipulation of the metric or the distance for Ospf, and I'm going to get rid of the manipulation of the distance in RIP. So again, now we're going to end up choosing the Ospf path over the RIP path. So if I do a trace route to 2.2.2.2 or even 2.2.3.2, I should see 3.2 should get through Ospf as well. I mean, not that it really matters, but I don't think, yeah. Router RIP. Why did that command not come out? Did I not do the no in front of those? I must not have. Take your time, guys. Whenever you're doing this stuff, take your time. Think about what it is you're trying to accomplish, because apparently I didn't do a no in front of those commands. I just cut and pasted them. All right, so now if I do a trace route to 2.2.2.2, we should go through router 3, and 3.2 should do the same thing. Okay, so now we're kind of back at our basic configuration. So let's say, for example, I just didn't even want to allow router 1 to learn about, and this is probably a very unique case because we would still want to have the redundancy, but let's say I just wouldn't want router 1 to learn about the 2.2.2 networks, or any RIP, redistributed RIP networks from its OSPF neighbor. So in this case, what I'm going to do is I'm going to apply a filter to the OSPF relationship between router 1 and router 3 and say, hey, don't send me these networks that are inside this domain, because I'm already part of that domain. I would say this is probably the least preferred method because you still want to have the redundancy, but I wanted to show you guys what it looks like anyway. So we're going to say IP access-list standard RIP routes in this case, and we're just going to deny 2.2.2.0, 0.0.1.255. So that's going to be the 2 and the 3 subnets, and we're going to permit every other route to come in. And then I'm going to go into the OSPF routing process, and I'm going to say distribute list RIP. Did I do dash routes? Yeah, dash routes in. So I'm applying a filter to my OSPF peer. All right. So now if I do a show IP route, I should have done this before I applied the filter, but we did our trace route, so you know that it was going the other direction. Now we're not getting the 2.2.2 route. 0, sorry. That's interesting. We should still be getting it from RIP. How come we're not getting it from RIP? Do show run section router. We should still be getting this route from RIP because we're only applying the filter to our relationship with OSPF. Could be a convergence thing. Show IP route 2.2.2.0. Yeah, it was. All right. It's just timing, right? Be patient. Distance vector protocols tend to be a lot slower than link state routing protocols. So we're getting the route from our RIP peer, but we're not getting the route from OSPF. In fact, if I do a show IP access-lists, you can see that we're actually getting matches against that particular, 2 routes match that particular wildcard. All right, and then we have 6 routes that match the other wildcard. All right. So that's another way. Like I said, this is probably not the most preferred method because if this fast Ethernet link between the RIP routers fails, then we're not going to have reachability through the OSPF domain. But we may have some other default routing capabilities or whatnot in that particular case. Okay. We can also use a distribute list to control what routes get installed in OSPF. Since OSPF is a link state protocol, the LSA is going to be propagated from one router to the other. All right. Now, you'll notice here, even though the route may not be in router 1, we don't have it in a routing information base. If I do a show IP OSPF database, let's see, let's get out of config mode so I can use my tab completion. Show IP OSPF database external for 2.2.2.0. We can see that the route is still there, right? It's in the database. We're learning about the 2.2.2.0 route. That's a difference. There's a difference between the way distance vector protocols work and link state protocols work. just because we're not using the route in our routing information base from a particular protocol doesn't mean that we're not actually seeing that route in the database. All right, the route is still present in the OSPF database. It's just not being installed in the RIB. All right. There's a more fancy way of using distribute lists as well. We can tie them to a routing protocol, and then we can define what is allowed to go in or out from that protocol into the routing protocol that we're currently configuring. So let's say we want to configure R2 so that the RIP routes are not allowed to be redistributed into OSPF. Again, this is a scenario that's going to kill our redundancy, but I'm just kind of running through different examples, if you will. So let's do a show run pipe section router. Oops, that's not going to work. Oh my gosh, there we go. All right. Let's go ahead and go into router OSPF1. No distance. Let's get rid of that. And router RIP. Well, we're not doing anything there. All right. This will be the last thing I'll show you guys, and we'll wrap it up. So let's say I go ahead and create another access list. IP access dash list standard RIP routes. We'll do the same thing on this case. We're going to deny the 2.2.2.0 network. I'll leave the 2.2.2.3. We're going to permit anything else. And now let's go into router OSPF1 and say distribute list distribute dash list. Let's do RIP routes. And let's see out of RIP. So in this case, what we're doing is we're applying a distribute list to the routes that are being sent out of RIP into OSPF. All right, so now we're applying a filter to the redistribution process as opposed to applying it to the neighbor relationship. All right, so there's all kinds of choices that we have, right? So I should be able to identify here now on router 1, ping 2.2.3.2, sorry, trace route, 2.2.3.2 goes directly to router 2. Let me get rid of the filter here, show run section router, because I want the OSPF route to be preferred. Config T router OSPF1 no distribute list. All right, there we go. So if I do a ping trace route 2.3.2, it should take OSPF, but 2.2 should take RIP. And that's because, again, we're applying a filter to the redistribution process. So the 2.2.3.0 loopback is being learned through OSPF, and the 2.2.2.0 loopback is being learned through RIP. We have a whole bunch of other options, guys. We can use prefix lists and apply a prefix list to a route map where we can actually tag routes. There's all kinds of things that we're going to see. So we'll wrap it up for this lesson, but in our next lesson, we're going to go ahead and take a look at some of those other scenarios, and I'll get into some more of the advanced scenarios and so on. All right, you guys good? We ready to wrap this up? We'll see you guys in the next lesson.